TMS320F28379D. Wow, bunch of words. We talked about that last time. This is TI as part. We'll probably call this a lot of times the 28379D. Oops, 9D. Or we'll call it the DSP. We'll call it the microcontroller, right? That's what will be when we talk about this guy. We will be using one other microcontroller later on, way later on in the semester. It's a 28027, but that's for later. Okay. Anyway, so we've got this microcontroller here in the middle of the red board, and then we've got those 80-pin connectors that you've already soldered the headers for. And they were kind of out here, right? Okay. Now, this chip, the 28379D, comes in a number of different packages. You can get a version that's got 176 pins coming off of it, and it's about 1 inch by 1 inch, so it's a little bit bigger than our Redboard's chip. It's quite amazing how many pins are on this little guy, but it's a bigger one. Now, the reason they do that, well, one, it's easier to solder. Like, it takes a while, but I could hand solder the one that all the pins come out on the side, right? Those kind of chips. It takes a little bit of practice or whatever. This chip that we have, I don't know if you noticed it, but it is just a square on our red board. All the pins for that guy are up underneath the chip in what's called a ball grid array. So when they manufacture that, if you had that chip and flipped it over before it was baked onto the board, you'd see a bunch of little solder balls. Kind of similar. Remember how we put solder on the resistor pad, right? And then we slid over the resistor when we were soldering, right? That's kind of the same idea. There's these little balls, little humps of solder underneath there, and the idea is the robotic tool, you know, or you have to have some kind of tool to line it up. Line it up. You plop it on the balls, or there's pads underneath there. So there's actually 357 pads underneath this thing. It's just crazy. And so the robot plops it on there, and then it sends it through an oven, and all those little balls connect to those pads of the red board, and that's how it's soldered on there. Okay, and then I'm sure this board is a couple layers thick, you know, 4 to 6 layers thick, and all those balls underneath there route out to where they need to be on this red board. Someone used a CAD package to route all that and design the red board, right, at Texas Instruments. Now again, so there's 357. If you look at your red board the next time, underneath, and we're not going to use this, maybe again, when I say we're not going to use it, I'm meaning in the labs. For your final project, we may find a reason to use it. I've used it for something. There's also a 60-pin connector, really tiny one, that's on the bottom of the board. And it's mainly for adding external memory to this device, to the red board. They bring out all the what are called external memory interface pins. And so TI, they must have been having some trouble with it because they don't sell it anymore. They used to sell a little board that could plug into this small connector on the bottom to add some RAM to this chip. Anyway, just kind of just showing you where are these 357 pins going out to, all right? Bunch of them. We do have a couple connectors that we're going to use on the end here. There is two sensor headers for optical encoders. That's how we're going to sense the position and speed of our wheels. And then there's another thing. We don't get into it in the lab, but there's a network called CAN, Controller Area Network, that I'm constantly trying to find a good sensor, a good use for it. If we were controlling a car, there's a great use for it. CAN is the bus throughout your whole car, right? There really isn't many hobby sensors or anything like that I can find for CAN. But anyway, another great project if you want to think about doing something with CAN. But anyway, okay, so we've got these 357 pins underneath. Now, of those 357 pins, a lot of those are power and ground too. You don't just have one pad where you bring power and ground into that chip. So ground and power are coming in. So, you know, I don't know how many, maybe 50 pins are ground and power, let's say. So you got 300 pins that need to get places. Well, as I said, right, we've got 80 pins here, right, at the headers, and then maybe another 60 pins here at the bottom approximately. So still we're not getting out all those 300 pins, and that's fine. In other words, TI, when they designed this launch pad, they decided what pins we needed and didn't need. Okay? And each pin is got a name for it, and its default name is either what general purpose I/O pin it is or what analog pin it is. So we have digital pins and analog pins. So each pin has a default state of a digital input. And so there is a pin called general purpose I/O pin 0. There's one called general purpose input pin 1, 2, 3, 4, etc. Right? And so we'll be calling those GPIOs. So GPIO 0, GPIO 1, 2, etc. Now, when we start digging into this, get deeper into lab 2, for example, you're going to see that there's GPIO 0, then 1, then 2, then 3. Then when we start getting out in the 20s and the 30s, you'll see there's a number of GPIOs that are skipped. Those are pins that are either going down to this bottom connector, the 60-pin connector, or just not getting anywhere. TI decided not to even route those pins. That's possible. Okay, so anyway, and I have a whole Excel spreadsheet we call the Mux Table, the pin Mux Table, and it labels all these GPIOs and what functions they can do and all this kind of stuff, and we'll get into that sheet. All this muxing of all the I/O pins. For lab 1 and lab 2, we're going to think of all the pins as GPIOs, general purpose I/O pins. We won't worry about serial port pins. We won't worry about PWM pins and all that yet. Right now, it's just a bunch of GPIOs, general purpose inputs and outputs. And I want to get into more what we're talking about, what's an input, what's an output. All right, and then, let's see, can we draw, I guess since I put the 2837 right there, we'll just kind of draw it like this. Your green board. Yeah, kind of. So here's the green board, or the breakout board. So now this is one that I designed in EagleCAD, okay? Not nearly as difficult of a design as the smaller red board. I didn't have to route 300 pins. I just had to route 80 pins, right, that come off those headers. And my pins, those header pins are spaced 0.1 inches, a tenth of an inch apart, right? That's so much easier than all those 300 pins being jammed into a little, what, 1.5 centimeter by 1.5 centimeter area, okay? So anyway, in other words, how are they doing that? They use really small traces, widths of traces, and all this good stuff. Okay, so what did I do? Well, the first thing I did on the green board is routed each header pin to a group of 3 pads. So this, 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 and you kind of saw that. And I'm blowing this up a little bit. Right? So this first pin right here on the header is connected to all 3 of those pads that you could solder to if you want to get connected to that header pin, right? And also the header pin on the other side is connected to 3 pads that you could solder to. Okay, so these are all connected. Connect, connect, connect. All right, and so on. And that's done for every header pin. But in addition, you know, we have all our LEDs over here. So in this little section of the board, we've got LEDs. Okay, And we'll talk about this, but there is you put these little chips down. Remember the 7404s? These chips, the 7404s, they drive current to the LEDs. Okay, and so what would happen is, if this is one of the general purpose I/O pins, I do route it for you to one of the 7404 chips, and then that pin then goes to one of the LEDs. And the way it's wired is like this. We have an LED with this being the anode, and then our 1K resistor to 3.3 volts. Anyway, we're going to draw that in more detail. But anyway, on what I'm just trying to show here is that I routed that GPIO pin to the correct spot on the 7404, and then the output pin in the 7404 goes to the LED. Okay, and that's all routed for you already on the board. Okay, and then, you know, all these other pins have their own purposes, and we have, again, in this Mux table, as we're going to call it, pin Mux table, we specify what all the meanings, what we're going to use each of those general purpose I/O pins for. Okay, good. All right, so now let's now blow up this idea of what we're doing with the LED and what we're doing with our push buttons too. Let's think about that. Okay, so that's kind of the breakout there, but now let's think about this. We've got a general purpose I/O pin, GPIO pin, let's see, I know GPIO pin 22, I know turns on and off an LED. It's connected to an LED. Okay? Now, with ours, with an Arduino, if you know this, Arduino uses 5-volt logic for its I/O pins. Most boards nowadays, and they do that just because it's nice, it drives more loads and all that kind of stuff. And there's chips. If we wanted to, we could have this board drive 5 volts. We'd need to just put a buffer chip in between, a voltage level converter is what they call it. But anyway, our I/O pins are 3.3 volt logic. Okay, and so if it's an output pin, so it can be both, right? That's what this I/O. This is general purpose input, and then or output. You can specify if you want it to be an input pin or if you want it to be an output pin. So to turn on and off an LED, what do you think? Now when we're talking about input and output, you always think you are the processor, right? When you think, because you know, if you're the LED, right, it needs an input, doesn't it, to turn it on. But if you're the processor talking to the LED, you need to be output, don't you, to turn on and off the LED. So whenever we're thinking about input output, we got to think of ourselves as the microcontroller. Okay, all right, good. So we use an output to turn on an LED. A push button, right? That creates a signal. That signal comes into the microcontroller. It's a very simple signal. It's just high or low, right? But that is an input. You would use an input for a push button. The levels here. So the input-output levels are controlled by what's called a standard TTL, transistor to transistor logic. And a low, again, I may not be exactly right on this spec, but it's somewhere, a low is approximately less than 0.5 volts. And it may be a little bit lower than that, but somewhere around there. So a low is when the signal is lower than 0.5 volt. Okay? A high signal is when the signal for sure is greater than 2.7 volts. But I have seen greater than 1.5 volts sometimes too. But in other words, you know, it's got to be greater than some threshold to be considered a high. Then there's this weird region in between there, isn't there? And that is a problem. If your signals aren't going above 1.5 volts or something like that, or 2.7, you're kind of in this weird region. Is it high, is it low type of thing. And just something's wrong with your circuit, in other words. It should be able to be driven that high and that low. Anyway, there's a thing called Schmidt trigger logic and all that kind of stuff that gets around all that problem if you have that problem on your circuit board. But anyway, so that's what we're going at, okay? So we can, and when we have a general purpose I/O pin, we can set it as an output, we can set it low. Now it's going to be low, it's going to be down at 0 volts. Maybe just a hair above 0 volts. You can measure it, right? You can take a digital multimeter and measure the voltage. And then when we drive it high, it's going to be something close to 3.3 volts. Maybe a little lower than that, 3.2 or something like that, depends on the circuit you're driving. Okay? And so when I say high, you know, and especially if you're thinking about how does that turn on the LED, you think that it's gone to 3.3 volts. When I say low, then you think that the signal is 0 or at ground, actually. Okay, so it's almost like it's connected to ground at that point. Yeah. So let's think about that. So now we've got this GPIO 222, and it comes out of the red board and then gets routed to our green board. And then this 7404 chip, and I think it's LV04 for low voltage. That just means 3.3 logic is the name of this. It's an inverter chip. It's got 6 inverters. And you sometimes draw just this with a circle. It's a logic inverter. And I'm running out of room. There's 6 of them. Okay, so it's a logic inverter. So I can drive 6 LEDs with this one chip, and given multiple inputs. Okay, so then the input, the GPIO 22, comes into an inverter, and then outputs here. Now, what does this LV04 do for us? It increases the amount of current. So this guy is connected to 3.3 volts. And it's connected to ground to power it, this chip. That's what you soldered down. And so because it drives extra current into this device. The 28 series board, its I/O pins cannot go much above 4 milliamps. And it's better to keep them down around 2 milliamps, if not lower. And if you're trying to drive a bunch of things, even that 2 milliamps can't be done when you're, say, driving 20 I/O pins, say, to drive LEDs and stuff like that. So you could actually damage the GPIO pin if you do not put this type of, you can think of it as like a buffer or a current drive, but it's really just a logic inverter to increase the current going to your LED. And LEDs need a little current, don't they, to be bright or whatever, to see them well. Okay, so that's all we're thinking there. But now let's look at this. So now we've got our LED. We're going to connect it here. So kind of draw this like this. Here's our LED. And then on the other side, we'll put LED here. On the other side is our resistor to 3.3 volts. And this is our 1K. Okay, now remember, what makes an LED turn on? It's when the voltage on the right side, I think that's the anode. I always get confused on that. One's the anode, one's the cathode, right? You help prove me wrong or whatever. I'm thinking this is the anode, this is the cathode, but I may be wrong on that. Whenever the voltage on the anode side is higher than the voltage on the cathode side, the LED turns on, right? And depending on how much difference in that voltage determines the brightness, doesn't it? Okay, so look at what happens. The GPIO 22 pin gets inverted. So let's say we set that pin high. Okay? The inverter inverts that. It's a logic inverter. So a high signal is low. A low signal is high. That's all an inverter means. Logic inverter. So this would become low. Agreed? Now, we've got, in a sense, ground on the left side. We've got 3.3 volts, don't we, through this current limiting resistor. On the right side, boom, the LED turns on. Okay? So by setting the I/O pin high, you turn the LED on. By setting the GPIO low, that makes this pin high, doesn't it? And so both sides are high, both sides are 3.3 volts, so the LED stays off, right? What do you think? So that is a way we'll use an output pin. Now, that's not the only way we could use general purpose output pins. We could also use that I/O pin to drive a transistor, for example. And we could turn on and off a transistor to whatever, to flip a switch so that a higher current load turns on a fan maybe, or something like that, right? You turn on a transistor, that then allows 12 volts to come through the transistor. That 12 volts can be applied to a little DC motor fan, and now you got a fan spinning. Okay? So I/O's outputs can be used for a lot of different things. We're going to use outputs for selecting different devices, different ICs, integrated circuits on our green board, in what's called a chip select. So we'll have different chips out there. Which one do we want to talk to? Well, the one that has its GPIO line low, its chip select line low. Okay? So we won't just be using digital outputs just for LEDs. Now we will for Lab 2, but we'll be using digital IOs for other things. So when you get to that point in the labs, you know, at about Lab 5 we start talking about chip selects. I'll say you handle the chip select just like you did an LED. Right? When you want to talk to the chip, you pull it low. Okay? Anyway, so that's kind of the output so how do we use an output, especially in Lab 2? Okay? Now, you guys may be familiar with Arduino. You know, in the setup function in Arduino, you had to say what each pin was doing. Is it an input? Is it an output? And all that kind of stuff. We've got to do the same thing in our main. GPIO 22 could also be an input. So we have to set that up in our main function to initialize our I/O pins. That's kind of the first thing we do in each of our labs. We kind of catalog what pins are we using, how are we using each of these different pins. Let's set up this pin mux so that it's the right state. It's the right type of pin that we want it to be. Okay, and we'll talk more about that. Right now, there's only two states, an input or an output. But later on, we're going to see that they can be serial ports, they can be PWMs, all that kind of stuff. Okay, so now inputs, I don't know if they're any more difficult, but another GPIO that we're going to be using, I'm pretty sure GPIO 7 we're going to set up to be an input. So, you know, you'll see me, when it's an output, you'll see me draw an arrow away from the processor, right? I'll point that way saying it's an output from the processor. When it's an input, okay, you'll see me doing the opposite. I'll go like this. And, you know, here is our 28379D. So it's an input into the 28379D. There's a number of, there's a couple different ways we could do switches, but we're doing the most simple one, just a momentary on-off switch. And so how do we wire this one? Okay, so we've got a switch out there, and you'll be soldering this probably this week. Not many of us got to the switches. So I'm going to draw it like this. You know, it's got a little contact right here. There's a little area on that. This is spring steel, right, that you can push down. Oops, oh my, that was not good. Spring steel that you can push down, right? See, that is a nice, ugly, handwritten switch there. Okay. Now, what we do with this switch is, you're going to see that we wire, well, it's already been wired for you on the green board. We put this side to ground on this switch. Okay? And then the GPIO input, GPIO 7 for example, is connected to the other pin of the switch. 2 pins on the switch, and then there's this little spring steel push button, right, that you can push down, hold it down. So now let's think about this. It's pretty obvious that what? GPIO pin 7, when the push button is pressed, is that at state 0 or state 1? High or low? Low, right? It's connected to ground, isn't it? So if we press this down and connect this, GPIO 7 is directly connected to ground. All right? What is it when we let off that switch? You would hope it's 3.3 volts, wouldn't you? You would hope it'd be high. Well, actually, when we let off, right now, the GPIO pin is what's called floating. Okay? It's not connected to anything. It's just a high impedance input. And if you get a little, you can actually put your fingers on it, and it may, because of your capacitance to somewhere else, right, it may turn that IO pin high, it may make it go low. Okay? So, what I did years and years ago on processors, old processors, there were chips that you could buy, surface mount or leaded chips, that had a gazillion resistors inside of them. Well, I should say gazillion. Let's say 10, what we call pull-up resistors. And you would have to wire a resistor. So look at this. So we've got this input coming into the processor. It's what's called, when it's set up like this as an input, it's called a high impedance input. And so you can think of inside the microcontroller, there is, where do I want to put this? Let's continue the pin into here. So inside the microcontroller, you can think of this as a high impedance input. So let's say 1 mega ohm to ground. Okay? Some input, a high impedance. Now, again, this still is floating. But what if now, before I get into the processor, into the pin of the processor, I put, going to my GPIO, I put a pull-up resistor right here. Oh, say 10K or something like that. Okay? Now think about what happens. So again, when the push button is pressed, the path of least resistance, right, 3.3, instead of dropping down to 1 mega ohm, 3.3 goes to ground, right? So this input is at 0 volts, isn't it? When the button's pressed, connected to ground. But now, when the button opens, right, we've got 3.3 dropping through 10 kilo ohms, but then the rest of it dropping through 1 mega ohms. This is a voltage divider. This is pretty darn close to 3.3 volts, isn't it? Because this impedance could even be bigger than 1 mega ohm even. You see what's happening? So now this is no longer floating. This is pulled up, is what we call it. So this is a pull-up resistor that allows this to happen. Now the cool thing, as I said, in old processors you had to solder a resistor like this on every pin that you wanted to have as an input. On ours, on this processor, we don't have to worry about the external interrupt. There is a switch, or a little transistor, whatever you want to call it, that you can actually attach an internal pull-up resistor. Let's put it up here, 3.3 volts. So we'll have to, you'll see this in lab 2, that we're going to have to enable the pull-up resistor for that IO pin. Okay? And by doing that, now it's no longer floating. We have the same circuit. Excuse me. This isn't a push button. This is just something you can programmatically change. Either you can connect the 3.3 the pull-up resistor to the IO pin, or you can disconnect it. Okay? You have this option when you're programming the device for that. Questions? Okay, so we're about out of time. Yeah, so we'll get into this a little bit more. Other thing, real quick, I got a little time. Other things that we'd be using for inputs. Again, yeah, we can use an input, a switch as an input. But there's other things too. For example, an event may happen. So you have an integrated circuit out there, and when a certain event happens, maybe X number of radians, the motor's moved X number of radians, I want to tell the processor, hey, this event happened. Well, you can have an IC pull an I/O line high or low. High says an event happened, low means no event happened, right? So it's not just, inputs are not just for switches. We can use them to communicate, or indicate that something is happening. Okay, good.